Hello everyone, we are Team NextGen and my name is Roshni Joga and my teammates are Praful and Mohib Khan. So the project we've built is a ResNet based waste classification model, which helps in classifying the recyclables, compostables and trash using deep learning techniques. Moving on to the next slide. So today we are excited to talk about an important challenge in waste management and how machine learning can play a critical role in addressing that. So, as highlighted in the problem statement, the effective waste classification is essential for promoting environmental sustainability. Accurate classification enables better recycling, conserves resources, and also reduces our reliance on the landfills. So, however, traditional manual wastage sorting methods are inefficient, which are labor intensive, and also they're prone to errors. So, often exposing workers to health risks. With increasing urbanization, waste streams are becoming more complex, making it even more harder for these conventional methods to meet sustainability goals. So, this is where the urgency for automated solution comes in. Our goal is clear. It is to develop a machine learning model that can accurately classify waste into three categories: recyclable, compostable, and trash. So, this automation can revolutionize waste management by making the process faster, safer, and more reliable. Moving on to the next slide, we have our dataset overview. So we've sourced it from UC Irvine machine learning repository. So there are two types of datasets here, the TrashNet dataset and also the real waste dataset. So here in the TrashNet dataset, we have over 3,800 training images, 950 validation images, and 4,700 test images. So, and here in the real waste dataset, we have 9 different waste types mapped into 3 main bins, which are recyclable, organic, and non-recyclable. So by combining insights from both datasets, we aim to improve the model's ability to generalize across real-world waste types. Moving on to the next slide, we have our pre-processing steps here. So to ensure the machine learning model performs optimally, we implemented a series of pre-processing steps. These can include pixel normalization, where this step applies normalization using ImageNet's mean and standard deviation values to align our data with pre-trained model standards. So the tensor flows preprocess input function handles this step seamlessly. And the second one is the data augmentation, where the techniques such as rotation, flipping, zooming were applied to artificially increase the size and diversity of our training dataset, improving the model's robustness too. So the image resizing are resized to 128 into 128 pixels to ensure compatibility with our model while maintaining computational efficiency. And the dataset splitting happens like this, where the training data is 80% and validation data is 20%, and with a separate test set reserved for final performance evaluation. So by combining these pre-processing steps, we are setting the foundation for an efficient and accurate waste classification model. Thank you, and moving on to the next slide.
As you can see, the base model for our application was ResNet, and the added layers were global average pooling for a feature extraction, fully connected layers or dense layers for classification, and then the output layer, softmax for class probabilities, and then for the optimization techniques we had SGD optimizer and then balanced class weights to address the class imbalance. So we'll dig deep into the model architecture and start with the defining ResNet. So, what is ResNet? ResNet is can be considered to be a ready-made brain that has already learned to identify patterns in images, like, for example, edges, textures, and shapes. So it helped us save time and effort by since it's pre-trained on millions of images. We use this to extract like important features from the base images. Um, we'll go on with the input layer first. So for the input layer, we had the images from the dataset of UCI that we resized to 128 by 128 pixels to make them consistent for the model. And then further, they were normalized using a special method called preprocess underscore input that was from a different Python library. And this was to make it compatible with the ResNet model, which was originally trained on a large dataset called ImageNet. And then we have the global average pooling layer. So what does this do? This layer basically takes all the detailed information that ResNet extracts from the images and compresses it into a simpler summary. So basically, what it does is it reduces the number of parameters. Uh, we can think of it as simplifying the data without losing the key information. And then we had the fully connected layers or the dense layers that were for classification. So what do these dense layers do? So after ResNet extracts the features, the dense layers help figure out which features belong to which class. We had three classes: trash, compostable, and then recyclable. So it defines which class has which features. And for this section, we to prevent the model from overfitting, we turn off some neurons randomly during training. And then we have the output layer. So what basically happens here, the model produces probabilities for each class, and the class with the highest probability is the model's prediction. So let's say if recyclable has the highest probability, then our prediction for the image would be recyclable. And then we have the optimization techniques. So basically these were used to improve the model's accuracy, and we use SED, or the stochastic gradient descent, to gradually adjust the model's parameters and improve its accuracy. What this does is it helps the model learn by comparing its predictions to the correct answers and minimizing the difference. Then we further balance the class weights to address a class imbalance. Since we had more images of some types than the others, we assigned weights to each class so that the model treats all classes equally. Another thing we did, as I mentioned about, would be augmentation. To make the model smarter, we added extra variety to the training images by rotating, flipping, or zooming them. So what this does is it basically teaches the model to handle different kinds of outputs. And how does it predict? So finally, when you give the model a new image, it reprocesses the image in the same way as during training, and then the image goes through ResNet, and the model predicts the class with the highest accuracy. And that's about it for our model architecture. I'll go on to the next slide. So this is the next slide I'll be going over, and we have model training and results. So for the training process, we tried a couple of different configurations and experimented and played around with it a lot. So we increased and decreased the number of epochs and had batch sizes. For example, we had a smaller batch size of 16, and we also trained with a larger batch size of 64. And then we played around with the callbacks. So we had early stoppage configured, and then we also had reduce LR on plateaus. So as soon as the validation loss increased to a certain plateau, then we would reduce the learning rate. And we also played around with the learning rates, and the best one we had was 0.001. That's when we got the highest accuracy. And the best model results we had were training accuracy was about 98%, and then validation accuracy was about 96%. And then for the same for the test data, we had 95.24%, and then for the test loss we had 0.1350. So this is a pretty good accuracy, but I feel like we could have done more. And basically the challenges we faced were 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 balancing the data set. I'm not sure how accurately the class weights work, but I feel like if we had more images of trash, and then we had equal images of all the three kinds, and it would have been a lot more accurate. Or as we aspire to build something that's mostly around close to 100%, and without any, like, without a lot of test loss. But this seems like a good model, since it has generalization. So it's not basic, it's not completely memorizing all the images. It has generalization, as we tested on foreign data, and it worked pretty well with it. So that's about it for our model training and results, and I'll pass on to my teammate Praful for the next slide.
Thank you so much, Mohib, for telling us about model training and results. So now we'll be talking about insights and visualization, particularly class activation maps, how used it in our project. So what it does is we visualize how the model focuses on relevant parts of the image classification. Uh, and there were some keen observation that we came to know by doing the class activation map, we discovered that there were some images for which the model was uh, giving some wrong predictions. So we tried to visualize what was going wrong. And further that, we hyperparameter tuned the model. So for this particular image, it was supposed to predict compostable, but it predicted the recyclable. And for this one, it predicted again compostable, and it was supposed to predict the recyclable for this. Moving on to the confusion matrix. So we tried to evaluate the model performance across different classes. So for the most part, we got recyclable correct. So it was kind of leaning towards the recyclable, and there was a strong classification with around 3013 correct prediction for recyclable, and there were minimal misclassification around 8 classified as recyclable, but it was supposed to classify it as compostable. So these are the actual ones. So there were 8 uh, predicted as recyclable, but it was supposed to predict that as compostable. There were 5 images there that was supposed to be predicted as compostable, but predicted as trash, and there were around 18 that was supposed to be predicted as recyclable, but predicted as compostable, and there were 651 images there was that was supposed to be predicted as recyclable but predicted as trash. Similarly, there were 22 images that were predicted as compostable but were supposed to be predicted as trash, and there were 63 images that were supposed to be predicted as trash but predicted as recyclable. So this was the confusion matrix. Moving on to model testing and deployment. So we in this process involves the uploading images and getting the prediction. So we kind of made a Gradio application, which I'll be further showing in the demo, how we uploaded the images and got the results. And we tested with numerous images across the internet. We tested random images that were foreign to the model, and the model accurately classified the images into the three categories, that is recyclable, compostable, and trash. So here are some sample images that I've attached. So this is a compostable type, this is a recyclable one, and these two are trash images. So for deployment, we built a user-friendly Gradio app interface to classify waste and deployed the Gradio app on Hugging Face spaces using the command line tool, the command line basically. And the app allows user to upload an image and receive a prediction in real time. So we'll be using Hugging Face spaces that ensures very easy access and scalability. For now, we have used the um, free version of Hugging Face where it gives us only 2 compute spaces. So what are the future improvements? So what we think that we can use data augmentation techniques to generate some synthetic data, and we can use for generating more data. And since we will have more data, we can train over that data, and we can move for generalization techniques as well, like using regularization as well. And we can incorporate some additional data sets for diversity, like we can go for some data that was not used for the model, like maybe using the metals, and maybe using some plastic images. And for model enhancement, we can use some really better architectures like efficient net. So these architecture required higher computing power. That is why we did not use for this particular project. And for deployment goal, we can use some real-time classification edge IoT devices, like a device that can actually be used for the garbage industry, like waste management. They must be using some IoT devices where we can install this, and the garbage can be easily classified using the image. So let's go on the project demo. So this is our application. I have added some images over here. Let's click on this one and hit the submit button. So it is showing 99.97%, and this is a compost garbage. Let's click on this one. This is a trash, and let's hit submit. It should give us trash. So it is giving us trash. Let's hit on this one, and it is giving trash. Well, let's go a step further and search for images. So I've searched for plastic images over the internet. This is a random image. I have saved this image. Let's go ahead and save image. Let's do, let's say, let's go to our model, clear this here. Let's upload this image, open it, and let's submit. So it is giving recyclable, which is right, with a 99.89% confidence, which is pretty great. Thank you so much for watching this video. This was a demonstration of the project we made, which is also called as Trash Classifier, and you can use this demo link. I'll attach the demo link on the canvas, and you can click and anytime come and run this application. Thank you.